4 light years away, something may be orbiting a star that looks almost exactly like our sun. Not a distant system buried in the outer spiral arms of the Milky Way. Not a faint red dwarf barely visible through a telescope, but the closest sun-like star to Earth. And for a brief moment in 2024, we may have seen a planet there. Then it vanished. On a clear night in the southern hemisphere, there's a bright point of light that doesn't look mysterious at all. It doesn't flicker uncertainly. It doesn't hide behind dust clouds. It shines with quiet confidence, steady and sharp. That light comes from Alpha Centauri. Astronomically speaking, close is almost never a useful word. The Milky Way stretches roughly 100,000 light-years across. Most of the stars we study lie dozens, hundreds, even thousands of light-years away. Their light began its journey before modern science even existed, but Alpha Centauri sits just over 4 light-years from Earth. If the entire galaxy were compressed into the size of a continent, Alpha Centauri would be closer than the nearest major city. In cosmic terms, it's not just nearby, it's next door. And yet, for nearly a century, it refused to answer one simple question. Does it have planets? By the early 2000s, astronomers had discovered thousands of exoplanets scattered across the galaxy. Giant worlds larger than Jupiter, rocky super-Earths hugging their stars, strange systems where planets orbit closer than Mercury, others where frozen giants drift in deep outer darkness. We learned how to detect the subtle gravitational tug of a planet pulling on its star. A tiny stellar wobble measured in meters per second. We learned to watch for minuscule dips in brightness when a planet crosses in front of its star, blocking less than 1% of the light. We even learned how to take direct images of massive young planets glowing faintly in infrared. Worlds hundreds of light-years away were mapped and cataloged. But the nearest sun-like system remained silent. It was an irony almost too perfect. We could measure planets orbiting stars whose light left before the invention of the steam engine. Yet the star shining in our own celestial backyard gave us nothing. No confirmed worlds, no stable detections, just noise. Part of the difficulty lies in what Alpha Centauri actually is. It's not a single star. It's a gravitational partnership. 2 stars, Alpha Centauri A and Alpha Centauri B, orbit each other in a slow, elegant dance that takes roughly 80 years to complete. Both are similar to our Sun. Alpha Centauri A, in particular, is nearly a solar twin in mass and temperature. At first glance, that similarity seems promising. If planets formed around our Sun, why not around a star so much like it? But binary systems complicate everything. Imagine trying to build a calm, orderly solar system, while another star periodically tugs on your protoplanetary disk. Gas and dust that might have settled gently into planets instead experience shifting gravitational forces. Stability becomes harder to maintain. For decades, theoretical models debated whether stable planets could even survive in the inner regions of such systems. And then there was another problem. Brightness. Alpha Centauri is the 3rd brightest star visible in Earth's night sky. That brilliance is beautiful to human eyes, but devastating to sensitive astronomical instruments. Trying to see a faint planet beside it is like trying to spot a firefly hovering next to a stadium floodlight. The glare doesn't just obscure the view. It overwhelms detectors. It scatters inside telescope optics. It creates diffraction patterns that look like phantom objects. Brightness, motion, and a crowded background of distant stars all combine into a perfect storm of observational difficulty. Because Alpha Centauri is so close, it also moves rapidly across the sky. Its proper motion is among the largest of any naked-eye star. That motion must be tracked with extraordinary precision. Even a microscopic targeting error can flood an observation with unwanted starlight. And behind it? the dense plain of the Milky Way. A backdrop filled with distant galaxies and stars that can masquerade as planetary signals. For decades, Alpha Centauri remained an enigma. Hints appeared from time to time. In 2012, a potential Earth-mass planet around Alpha Centauri b was announced. Excitement surged. Headlines spread. But deeper analysis suggested the signal was likely noise embedded in stellar activity data. Hope rose. Then it collapsed. In 2019, astronomers using ground-based instruments reported a faint possible signal near Alpha Centauri A. It was labeled cautiously, never confirmed. Atmospheric turbulence could mimic such detections. Again, the system retreated into ambiguity. Alpha Centauri became a symbol of proximity without knowledge, close enough to imagine visiting, too elusive to understand. And that's why the launch of the James Webb Space Telescope changed the stakes. Webb was not built to study bright nearby stars. It was engineered to look backward in time, to detect the faint infrared glow of the first galaxies that formed after the Big Bang. Its mirrors were polished to capture ancient, stretched light that had traveled for billions of years. It was optimized for darkness, cold, silence. Alpha Centauri is none of those things. It is bright, aggressively bright. Pointing Webb at it was like using night vision goggles to stare at a searchlight. The risk wasn't just poor data. It was saturation, overexposure, permanent damage to sensitive detectors. So why attempt it at all? Because planets don't just reflect light, they glow. When a planet absorbs energy from its star, it re-emits that energy as heat. Even cold worlds radiate faint infrared radiation, invisible to human eyes, but detectable to an instrument precisely tuned for those wavelengths. If a mature gas giant orbited Alpha Centauri at the right distance, it wouldn't blaze like a newborn planet. It would whisper. And Webb was designed to hear whispers. Inside Webb is an instrument called MIRI, the mid-infrared instrument. At wavelengths around 15 micrometers, objects with temperatures between 200 and 300 Kelvin radiate measurable heat. Well, that's roughly the temperature range expected for a gas giant orbiting in the outer temperate zone of a sun-like star. But detecting that faint warmth requires suppressing the overwhelming glare of the host star. Enter the coronagraph. A coronagraph acts like an artificial eclipse. It blocks the central light of a star inside the telescope, dramatically reducing glare and allowing faint nearby objects to emerge. It cannot eliminate starlight entirely. Physics forbids that. But it can dim it enough to reveal companions thousands of times fainter. Using Webb to observe Alpha Centauri required extreme care. Engineers developed a technique called blind offset pointing. Instead of locking directly onto the blinding star, Webb first aimed at a nearby reference star of manageable brightness. Once stabilized, it shifted its aim by a precisely calculated distance, placing Alpha Centauri behind the coronagraph mask. Every variable had to be accounted for: proper motion, parallax caused by Earth's orbit, the orbital position of Alpha Centauri b. Months of simulations preceded the attempt. Because this was more than just another observation. It was the first serious attempt to directly image a mature planet around the nearest sun-like star. August 2024. Webb stared for hours. Infrared photons that had traveled more than 4 years through interstellar space poured into its detectors. Data streamed back from its orbit nearly 1 million miles from Earth. At first glance, the raw images looked chaotic. Diffraction spikes radiated outward. Residual glare formed halos and streaks. Noise patterns overlapped in tangled layers. To an untrained eye, it looked like abstract art. But astronomy is not about what appears first. It's about what remains after everything else is subtracted. Layer by layer, scientists removed systematic artifacts. They compared reference stars. They modeled diffraction behavior. They peeled away structured noise. And beneath the suppressed glare, a faint point of warmth appeared. Small, stable, located just beyond the brightest region of residual starlight. It wasn't dramatic. It wasn't blazing. But it was there. Roughly 10,000 times dimmer than the star beside it, and statistically strong enough that random noise was extraordinarily unlikely. For the first time in history, something had been detected in the inner region around Alpha Centauri A that behaved like a planetary signal. The team gave it a cautious label, S1. Not planet, not yet, just Source 1. If real, S1 lay about 2 astronomical units from Alpha Centauri A, roughly twice the Earth-Sun distance. Its infrared brightness suggested a temperature between 200 and 250 Kelvin. Cold, but consistent with a gas giant warmed by a sun-like star at that distance. It would not be a hot Jupiter, not a newborn glowing world, but a mature, billion-year-old giant orbiting quietly in the temperate region of the nearest sun-like system. If confirmed, it would be historic, because direct imaging has almost always favored young, massive planets far from their stars, bright and widely separated. S1 appeared older, cooler, closer, exactly the type of planet astronomers once thought impossible to directly image in such a bright nearby system. But science is cautious. Every alternative explanation had to be dismantled. Could it be a background galaxy aligned by coincidence? Catalog searches revealed nothing. Could it be an asteroid drifting through our own solar system? Its position remained fixed relative to Alpha Centauri during hours of observation. Could it be an instrumental artifact? Artificial planet signals injected into the data behaved similarly to S1. Noise did not. Still, one rule remained. Planets move. If S1 orbited Alpha Centauri A, it would not stay fixed in place. Over time, it must shift position in accordance with Kepler's laws. And that motion would become the ultimate test. Follow-up observations were scheduled. If S1 appeared again, slightly shifted along a gravitational arc, the case for a real planet would strengthen dramatically. If it did not, then something far stranger was happening. Because planets can be faint, they can be cold, they can hide in glare, but they do not simply cease to exist. And yet, that is exactly what would seem to happen next. The problem wasn't finding a planet. The problem was surviving the star. The James Webb Space Telescope was never designed to stare at something like Alpha Centauri. Webb was built for darkness, for ancient light stretched thin by cosmic expansion, for galaxies so far away their glow barely registers against the cold of space. Its entire architecture, the segmented gold mirrors, the multi-layered sunshield, the cryogenic instruments, was engineered to detect whispers from the early universe. Alpha Centauri is not a whisper. It is a shout, a blazing, unfiltered flood of photons only 4 light-years away. Pointing Webb toward it was like turning a deep-sea exploration camera toward a welding torch. Too much light doesn't just ruin data. It saturates detectors. It bleeds across pixels. It creates artifacts that masquerade as structure. And worst of all, it can permanently damage the instrument. Every observation with Webb is precious. There is no servicing mission waiting in orbit. No astronaut will ever replace a failed detector. This telescope operates nearly 1 million miles from Earth, near the Sun-Earth L2 Lagrange point, a region of gravitational balance where it can maintain thermal stability and uninterrupted views of deep space. To risk it on one of the brightest stars in the sky required more than curiosity. It required confidence. The key lay in heat. Planets, even cold ones, emit thermal radiation. A gas giant orbiting a sun-like star absorbs energy and re-radiates it in the infrared. At wavelengths around 10 to 20 micrometers, even a world hundreds of degrees below freezing becomes detectable, if the glare can be suppressed. That is where MIRI enters the story. MIRI, the mid-infrared instrument, is Webb's coldest, most sensitive eye. It operates at temperatures near absolute zero, shielded behind layers of insulation so delicate that a slight increase in heat could degrade performance. MIRI can detect objects with temperatures similar to the outer planets in our solar system. But detecting faint warmth beside Alpha Centauri required something more. It required an eclipse inside the telescope. The coronagraph. Inside Webb, a tiny mask blocks the central light of a star. It's an artificial solar eclipse engineered at microscopic precision. Imagine placing a coin exactly over a street lamp while trying to see the dim outline of a passing bird beside it. You cannot eliminate every photon. Light bends, it diffracts, it sneaks around edges. But if you block enough of it, something faint might emerge. Coronagraphy is not magic. It is subtraction. It suppresses starlight by factors of thousands. But Alpha Centauri demanded suppression near the limits of physics. Even with the mask perfectly aligned, residual glare would ripple outward in diffraction rings and spikes, optical fingerprints unique to each observation. And alignment was the most dangerous step of all, because Alpha Centauri moves. Unlike distant background stars that appear almost fixed, Alpha Centauri drifts noticeably across the sky due to its proximity. Its proper motion is enormous by astronomical standards. If the star were misaligned by even a fraction of an arcsecond, a sliver of sky smaller than the width of a coin seen from kilometers away, light would leak past the coronagraph. Leakage would mean saturation. Saturation would mean lost data, or worse. To avoid that, engineers devised a strategy known as blind offset pointing. Instead of pointing directly at Alpha Centauri, Webb would first lock onto a nearby reference star, dim enough to be safe. Once stabilized, the telescope would execute a precisely calculated shift. No real-time visual confirmation, no direct feedback from the bright star. Just mathematics. It was like navigating into a blinding spotlight while closing your eyes, trusting only your instruments. Every variable had to be calculated in advance. The exact position of Alpha Centauri at that moment in 2024. Its proper motion. The parallax caused by Earth's orbit around the Sun. Even the orbital phase between Alpha Centauri A and its companion, Alpha Centauri B. Because that companion star presented another complication. Alpha Centauri A does not shine alone. Alpha Centauri B orbits close enough that its light can contaminate observations. Even if A were perfectly masked, B's photons could scatter across the detector, producing complex halos and interference patterns. No coronagraph can suppress two bright stars at different positions simultaneously. So scientists had to anticipate contamination, model it, simulate it, subtract it later. Months before the August 2024 observation, teams ran virtual rehearsals. Computer simulations predicted how diffraction patterns would appear. Engineers injected synthetic planets into test data to see whether the system could recover them. They tested failure scenarios. What if alignment drifted? What if thermal fluctuations altered optical performance? What if subtle detector noise mimicked a planetary signal? Every answer had to be prepared before the telescope ever turned. Because once the observation began, there would be no second chance in that same window. August 2024. Webb rotated slowly into position. Its sun shield remained perfectly oriented toward the sun, protecting its instruments in perpetual shadow. its golden mirrors adjusted minutely, compensating for thermal and mechanical variations. First, the reference star. Lock acquired, stability confirmed. Then the blind offset, a silent shift through space. Alpha Centauri slid behind the coronagraph mask. For a moment, nothing dramatic happened. No explosion of light, no alarm, just the quiet accumulation of photons. Exposure after exposure. Infrared radiation that had left Alpha Centauri 4 years earlier now arrived at a detector cooled to a few degrees above absolute zero. Hours passed. In space, patience is routine. On Earth, tension grew. The first raw images returned looked nothing like discovery. They looked like chaos. Bright diffraction spikes radiated outward in cross-shaped patterns. Concentric rings shimmered around the masked star. Streaks from Alpha Centauri b cut diagonally through the field. Background stars flickered faintly. Detector noise layered itself across the image like static. To the untrained eye, it resembled abstract art, not planetary science. But astronomers are trained to distrust first impressions. Raw images are never the truth. They are the sum of optics, physics, electronics, and environment. Discovery lives in subtraction. The team began with reference star differential imaging. They observed other stars under identical instrument settings, building a template of how Webb behaves when no planet is present. These templates captured systematic patterns, diffraction fingerprints, thermal noise structures, detector quirks. Then those patterns were subtracted from the Alpha Centauri data, layer by layer. Each subtraction removed known artifacts. What remained grew cleaner, still chaotic, but less so. Next came principal component analysis, mathematical decomposition of correlated noise structures. Patterns that repeated across exposures were isolated and removed. Independent subsets of the data were processed separately to avoid bias. If a signal persisted across subsets, it was less likely to be noise. Hours turned into days of analysis. Every time a layer was removed, something faint became slightly clearer. Or so it seemed. Because the danger in such analysis is self-deception. The human brain is wired to see structure in randomness, faces in clouds, patterns in static. So the team blinded portions of the dataset, analyzing sections without knowing whether synthetic planets had been inserted. If they could recover artificial signals reliably, confidence would grow. If false positives emerged too easily, the detection would be suspect. The pipeline held. Synthetic planets were recovered. Noise behaved differently. And then, in one processed frame, a faint point of warmth appeared. It was small, barely above background, but stable, consistent in position across independent data subsets, roughly 1.5 arcseconds from Alpha Centauri A, just outside the region where coronagraph suppression is strongest. Its brightness in the mid-infrared corresponded to an object far cooler than a young, glowing exoplanet, but warm enough to be consistent with a mature gas giant. Statistical analysis followed. Signal-to-noise ratios were calculated. False positive probabilities estimated. The detection crossed the threshold considered significant by astronomical standards. Not marginal, not tentative, strong, but not yet definitive. Because science does not celebrate too early, every extraordinary detection demands extraordinary scrutiny. The team did not announce a planet. They labeled the signal cautiously S1, Source 1, a placeholder name for something that might not survive further testing. Yet even before confirmation, something profound had already happened. For decades, Alpha Centauri represented a wall of glare, an untouchable lighthouse in the sky. Now, for the first time, humanity had looked directly into that light and seen something faint beside it. Whether S1 was a planet, a background object, or an elaborate illusion, Webb had proven a point. The glare was penetrable. The nearest sun-like star was no longer observationally off-limits. A boundary had been crossed, and with that boundary came a new question. If something appeared once, would it appear again? Because if S1 truly orbited Alpha Centauri A, it would not remain frozen in place. Gravity would pull it along a path, a curved arc, a predictable motion, and that motion would either confirm its reality or expose it as a ghost. Follow-up observations were scheduled for early 2025. The expectation seemed simple. If S1 was real, it would still be there. Perhaps slightly shifted, perhaps dimmer, but present. No one was prepared for what would happen next. They didn't celebrate. Not at first. In astronomy, the moment of apparent discovery is often the most dangerous moment of all, because that's when expectation begins to whisper. And expectation can be louder than data. The faint point beside Alpha Centauri was not dramatic. It didn't flare, it didn't pulse, it didn't announce itself. It simply persisted. Roughly 1.5 arcseconds from Alpha Centauri A. At that distance, given the system's proximity to Earth, the separation translated to about 2 astronomical units, twice the distance between Earth and the Sun. That number alone raised eyebrows. 2 AU sits near the outer region of the habitable zone for a star slightly brighter than our Sun. Not in the blazing inner furnace, not in the frozen outskirts. In a dynamically stable, theoretically survivable region. If a planet were going to exist around Alpha Centauri A, that's exactly where models suggested it might live. But suggestion is not confirmation. The team began dismantling their own discovery. The first suspect was coincidence. The Milky Way's plane is crowded. Behind Alpha Centauri lies a dense star field, interwoven with distant galaxies. A background galaxy, perfectly aligned along the line of sight, could appear as a faint, unresolved point. So they searched archival sky surveys. No known galaxy occupied that position. Older datasets showed nothing persistent at those coordinates. If it were a background object, it would not move relative to distant stars over time. But this signal's position was tied precisely to Alpha Centauri A within the observation window. That made coincidence less likely. Next suspect. Foreground contamination. An asteroid drifting through our own solar system could masquerade as a point source. But asteroids move, even distant ones shift noticeably over hours. The August 2024 data spanned long exposures. S1 did not drift. It remained fixed relative to Alpha Centauri A across the observation sequence. Foreground object ruled out. Then came the most uncomfortable possibility: instrumental illusion. Coronagraphs are powerful, but they are not perfect. Residual speckles, tiny bright spots caused by diffraction and imperfect wavefront correction, can mimic planets. Some speckles are transient, others persist. Distinguishing a real astrophysical source from an optical artifact requires statistical brutality, so the team attacked the data from every angle. They reprocessed it using independent pipelines. They varied subtraction parameters. They adjusted noise thresholds. They masked different regions of the detector. If S1 were an artifact, it would behave differently under different reductions. It didn't. It remained. Faint, but stable. To push further, scientists performed injection recovery tests. They took the raw data and inserted artificial planetary signals at various positions and brightness levels. Then they ran the entire processing pipeline blind. If the algorithm could reliably recover injected planets and ignore noise, confidence would rise. It did. Injected signals behaved like S1. Noise did not. Speckles smeared differently. Artifacts shifted with processing choices. S1 did not. It maintained consistent photometric and positional characteristics. The statistical significance reached the level astronomers refer to as 5 sigma, meaning the probability of the signal being a random fluctuation was extraordinarily small. Not impossible, but vanishingly unlikely. Still, 5 sigma does not equal truth. History has taught astronomers humility. Signals once celebrated have later evaporated under deeper scrutiny. The universe is subtle. Instruments are complex. Data can deceive. And so the label remained cautious. S1. Source 1. Then came the physical interpretation. If S1 were a planet, what kind of planet could it be? The brightness measured at roughly 15 micrometers offered the first clue. Thermal emission at that wavelength suggested a temperature between 200 and 250 Kelvin. That's around minus 50 degrees Celsius. Cold by human standards, but warm for a gas giant orbiting 2 astronomical units from a sun-like star. This was not a hot Jupiter, not a blistering world hugging its star. Nor was it a newborn planet glowing from leftover formation heat. Alpha Centauri is about 5 billion years old, similar in age to our Sun. Any planets there would be mature, cooled, quiet. S1's temperature fit that expectation. Its estimated luminosity suggested a mass roughly comparable to Saturn, perhaps between 80 and 150 Earth masses, large enough to accumulate a thick hydrogen-helium envelope, not massive enough to ignite fusion. A true planet, not a failed star. If correct, this would be revolutionary, because direct imaging traditionally favors young, massive planets far from their stars. Such planets are bright and widely separated, easy to see. S1 was neither. It was older, cooler, closer. Exactly the kind of world many thought beyond the reach of direct imaging in such a bright system. It was like spotting a dim porch light beside a lighthouse beam. Possible, but extremely difficult. And then there was orbital geometry. At roughly 2 astronomical units, ES1 would lie in a dynamically stable region around Alpha Centauri A. Binary star systems complicate planetary stability. The gravitational pull of Alpha Centauri B periodically perturbs the region around A, but simulations over decades have shown that stable orbits exist within a few astronomical units of each star. S1's position fell squarely within that predicted safe zone. That alignment between observation and theory was unsettlingly neat. Too neat, some thought. Nature is rarely that cooperative, but sometimes it is. Excitement grew cautiously within the team. If confirmed, S1 would become the closest directly imaged exoplanet candidate ever detected, closer than any planet ever photographed around another star. Orbiting the most realistic interstellar destination humanity has. For generations, Alpha Centauri has been the fictional first stop beyond our solar system. Now it might host a Saturn-like giant in its temperate zone, but excitement was tempered by a single, unbreakable rule: planets move. If S1 truly orbited Alpha Centauri A, it would not remain stationary. Over months, it would shift along its orbit according to Kepler's laws. The speed and direction of that shift would depend on its orbital period, eccentricity, and inclination. But motion was inevitable. That motion would either confirm its planetary nature or expose it as illusion. Follow-up observations were scheduled for early 2025. The expectation seemed straightforward. S1 should still be visible, perhaps slightly displaced along a curved arc, perhaps a bit closer or farther from the star, but detectable. Astronomers ran orbital simulations. Short-period orbits would produce noticeable motion within months. Longer-period orbits would produce subtle shifts. Even eccentric orbits, stretched ellipses rather than near circles, would still keep the planet within visible range in most configurations. Very few plausible orbital solutions predicted complete disappearance. The working assumption was clear. If S1 was real, it would show itself again. Outside the team, rumors began to circulate. Nothing official, nothing published yet, but whispers travel quickly in the astronomical community. If Webb had truly detected a mature gas giant around Alpha Centauri A, it would mark a turning point. The nearest sun-like star would no longer be a blank page. It would be a planetary system. That realization carried weight beyond science. Alpha Centauri is not just another catalog entry. It is a familiar star. Navigators have used it for centuries. Science fiction writers have sent generation ships toward it. Engineers designing laser-driven light sails cite it as the first realistic interstellar target. A confirmed planet there would shift imagination into something more concrete, a destination. But first, it had to survive February. The early 2025 observing window arrived. Webb once again rotated into position. The blind offset procedure had already proven successful. The coronagraph held steady. Exposure times matched or exceeded those of August. Sensitivity was at least as good. If S1 was there, Webb would see it. Data streamed back to Earth. Processing began immediately. Scientists focused first on the predicted region. The area where orbital simulations suggested S1 should now lie. Nothing. No faint glow. No statistically significant signal. They widened the search. Perhaps orbital motion had shifted it more than expected. Simulations were updated. Alternate positions examined. Still nothing. They reprocessed the data from scratch. Different noise models, different subtraction parameters. Independent teams ran blind analyses to avoid confirmation bias. The result remained unchanged. The frame showed only glare and darkness. S1 was gone. At first, the team assumed orbital geometry might explain it. Perhaps the planet had moved closer to the star, while entering a region where residual glare overwhelmed its faint thermal emission. Perhaps it was hiding within a blind spot of the coronagraph's contrast profile. But the absence was stark. The signal that had crossed statistical significance in August 2024 simply did not appear in February 2025. April offered another opportunity, another observation, another attempt. Again, nothing. The region where S1 had once glowed faintly now showed only noise. The closest directly imaged exoplanet candidate in history had evaporated. Silence settled over the analysis. Not the silence of failure, the silence of confusion. Because planets do not vanish, they orbit, they shine, they cool, they persist. If S1 had been an illusion, then August 2024 represented a statistical ghost, a rare alignment of noise masquerading as structure. If it was real, then something more subtle was happening. Something governed not by disappearance, but by geometry. The story was no longer about detection. It was about motion. And motion would either resurrect S1 or bury it forever. The second time, they expected confirmation. Instead, they found emptiness. February 2025 did not begin with drama. There were no alarms, no technical failures, no anomalies in spacecraft telemetry. The James Webb Space Telescope performed exactly as designed. The blind offset procedure locked with precision. The coronagraph alignment was clean. Detector sensitivity matched, even exceeded, the August 2024 observation. From a purely engineering standpoint, it was flawless. If S1 existed, this should have been the easiest part. Because planets don't fade in a few months. They don't cool by hundreds of degrees overnight. They don't dissolve into vacuum. They move. And movement is predictable. The team began with orbital expectations. Based on its August position, roughly 2 astronomical units from Alpha Centauri A, astronomers had simulated thousands of possible orbital paths. Circular orbits, slightly elliptical ones, highly inclined planes, even moderately eccentric configurations. Almost all plausible solutions suggested the planet would still be visible in early 2025. Perhaps slightly shifted along its arc. Perhaps marginally closer to the star. But detectable. The geometry did not suggest disappearance, not this quickly. Data arrived. Processing began. The subtraction pipeline, refined over months, executed step by step. Reference star differential imaging, principal component analysis, noise modeling, artifact suppression. Each layer peeled away the glare of Alpha Centauri A. The region of interest emerged, and there was nothing there. No faint point, no warm glow, no signal exceeding background noise, just structured residual light and the familiar diffraction halo. They expanded the search radius. Perhaps the orbital period was shorter than expected. Perhaps S1 had moved farther along its arc. Simulations updated in real time. New coordinates tested. Still nothing. There is a particular tension in moments like this. Not panic, not despair. A tightening of analytical focus. Because scientists do not jump to conclusions. They interrogate them. Could sensitivity have dropped? No. Instrument metrics showed nominal performance. Could noise suppression have accidentally erased the signal? Reprocessing from scratch yielded identical results. Independent teams ran blind analyses. No one found it. The signal that had passed 5 sigma confidence in August was absent in February. April 2025 offered one more opportunity within the seasonal window. If February had caught the planet near an unfortunate alignment, perhaps temporarily buried in glare, April might restore visibility. Webb observed again. The procedure was now routine. Confidence in technique was high. If anything, analysis was faster. Oh, sharper, more skeptical. The result did not change. S1 did not reappear. 2 follow-up observations, 2 null detections. At this point, the simplest explanation began to loom. Perhaps August 2024 had been a statistical anomaly. Even 5 sigma events, while rare, are not impossible. Astronomical history contains examples of signals celebrated prematurely, later reclassified as noise. Instruments operate at extreme sensitivity. They measure photons that barely exist above background. And sometimes, structure emerges from randomness. The universe does not owe us clarity. But something about S1 resisted that tidy dismissal. Because artifacts behave in certain ways, they flicker across data subsets. They smear under parameter changes. They drift when algorithms are adjusted. S1 had not behaved like that. It had been stable, consistent, photometrically coherent, and its brightness matched physical expectations for a cool gas giant. If it was noise with remarkable discipline, so the team turned to geometry. Because detection is not just about brightness, it's about contrast. A coronagraph does not suppress light equally in all directions. Its performance varies across the field. Some angles achieve exceptional contrast. Others remain contaminated by residual diffraction patterns. Imagine shining a flashlight through a narrow opening. The beam is not uniform. There are bright arcs and dimmer patches. An object drifting through that beam could appear brilliant in one region and vanish in another, even though it never changed at all. If S1 followed a highly eccentric orbit, its separation from Alpha Centauri A would vary significantly over time. At its farthest point, a pastron, it would sit at maximum angular separation, easier to detect, closer to the coronagraph's sweet spot. But as it moved toward periastron, its closest approach, it would slide into regions dominated by residual glare. There, the faint infrared glow of a Saturn-mass planet might be overwhelmed, not destroyed, not dimmed, simply concealed. Orbital simulations intensified. astronomers generated millions of potential trajectories consistent with the August detection. They varied eccentricity from near-circular to highly elongated. They altered inclination relative to our line of sight. They tested orbital periods between 1 and 10 Earth years. Then they asked a new question. How many stable orbits would produce exactly this pattern? Visible in August 2024. Invisible in February and April 2025. The answer surprised even the skeptics. More than half of dynamically stable orbital configurations produced precisely that outcome. In many scenarios, S1 would have been near Apastron during August, sitting in a high-contrast region. By early 2025, it would have moved inward along an elliptical path. Its angular separation would shrink. Its location would fall into a zone where coronagraph contrast drops below detectability. The planet would still exist. Webb simply would not see it. The disappearance was not destruction. It was geometry. This possibility reframed everything. Instead of contradicting the planet hypothesis, the null detections strengthened certain orbital models. Non-detection in early 2025 became statistically plausible, even likely, under eccentric solutions. And the story gained another layer, because there had been an earlier whisper. In 2019, astronomers using ground-based instruments had reported a faint candidate signal near Alpha Centauri A. It was labeled cautiously C1, never confirmed. Atmospheric turbulence often mimics faint planetary signatures. The detection faded into uncertainty. But C1's reported position was closer to the star than S1's August location. What if they were not separate signals? What if they were glimpses of the same world at different points along a stretched orbit? When orbital models incorporated both 2019 and 2024 positions, something remarkable happened. A family of solutions emerged. Highly eccentric orbits, with eccentricity near 0.4, satisfied both detections. Such an orbit would produce dramatic changes in separation over just a few years. In 2019, the planet might have been closer in. In 2024, farther out. In 2025, sliding back toward the star. Hidden. An eccentricity of 0.4 is not extreme by exoplanet standards, but it is far more elongated than Earth's nearly circular path. It implies substantial variation in stellar irradiation over each orbit. An orbital period between 2 and 3 Earth years would fit the timeline. Such a world would not move slowly and predictably like Jupiter. It would swing, accelerating near Periastron, lingering near Apastron, crossing detectability thresholds like a pendulum moving through beams of light. Under these solutions, the disappearance was not a failure, it was expected, and it pointed toward something real. But expectation is not proof. The only way to confirm S1 would be to predict its return. If the eccentric orbit hypothesis was correct, the planet would eventually swing outward again, back toward Apastron, back into Webb's high-contrast region. Simulations converged on a window, mid to late 2026, roughly 2 years after the August detection. If S1 were real, it should reappear near a predicted position along its elliptical arc. The universe, in effect, had set a date. That realization shifted the emotional landscape. The question was no longer, did we imagine it? The question became, will it come back? Because if Webb observes Alpha Centauri in 2026 and finds S1 near the predicted coordinates, the case becomes overwhelming. Random noise does not trace gravitational ellipses across years. Background galaxies do not orbit nearby stars. Instrument artifacts do not obey Kepler's laws. But if 2026 passes and the field remains empty, then the August detection will retreat into the category of statistical ghost. Either way, the mystery narrows. It becomes testable, measurable, finite. For now, S1 exists in a strange state, detected once with strong confidence, absent twice under excellent conditions, compatible with eccentric orbital motion, incompatible with circular stability. It is not confirmed, not dismissed. It occupies a liminal space between world and illusion. And somewhere, 4 light-years away, Alpha Centauri A continues to shine, unaware, indifferent. Its potential planet, if real, continues its orbit without drama. It does not know it has been named. It does not know it has disappeared from our view. It simply follows gravity, as it always has. The story now hinges on patience, because the next time Webb looks, at precisely the right time, from precisely the right angle, the answer will not be ambiguous. Either a faint point of warmth will step back into visibility, or the darkness will remain unbroken. If S1 was real, then it wasn't gone. It was hiding. By mid-2025, the debate had shifted. The question was no longer whether the August 2024 detection had statistical strength. It did. The question was whether physics could explain its disappearance without invoking illusion. And physics, unlike speculation, is predictable. Gravity does not improvise. At first glance, the vanishing seemed fatal to the planet hypothesis. 2 clean follow-up observations, 2 empty frames, no faint infrared warmth, no source. But when astronomers overlaid Webb's coronagraph contrast map onto the projected orbit of S1, a new pattern emerged. Webb does not see equally in every direction. Its coronagraph suppresses starlight most effectively in specific angular regions. Between those regions, contrast performance drops. Residual diffraction rings create invisible barriers, zones where faint objects drown in structured glare. To the naked eye, the processed image looks uniform. To an expert, it is a terrain map of sensitivity, peaks, and valleys. If S1 had moved into one of those valleys, it would vanish. Not because it ceased to exist, but because it slipped below detectability. Imagine standing in a dark valley at night while someone sweeps a searchlight across the hills. If you stand at the right angle, you glow brilliantly. Take 2 steps sideways, and the beam no longer touches you. You are still there, but unseen. That is coronagraph geometry. The August detection placed S1 near a region of relatively high contrast, a sweet spot just outside the most intense residual glare from Alpha Centauri A. In February and April 2025, orbital models suggested it may have drifted inward along an elliptical arc. Closer angular separation, worse contrast. Lower signal-to-noise ratio, the difference did not need to be dramatic. A change of a few tenths of an arcsecond could push the planet into invisibility, and that was entirely consistent with an eccentric orbit. The simulations became more aggressive. Instead of asking, could this explain it? They asked, how likely is this scenario? Millions of orbital solutions were generated. Each one had to satisfy the August 2024 detection position, stable dynamics within a binary star system, non-detection in February and April 2025, plausible mass and luminosity constraints. The result was startling. A large fraction, over 50%, of stable orbital configurations produced exactly this pattern. Visible once, hidden twice, reappearing later. In many of those solutions, S1's orbit had an eccentricity near 0.4. That means its distance from Alpha Centauri A would vary dramatically during each revolution. At Apastron, its farthest point, it would sit comfortably in a high-contrast region. At Periastron, closest approach, it would plunge into glare. The disappearance was not random. It was orbital choreography. But the story grew stranger, because this might not have been the first time humanity glimpsed this world. In 2019, years before Webb ever looked at Alpha Centauri, Astronomers using the European Southern Observatory's Very Large Telescope reported a faint candidate signal. They called it C1. The detection was tentative. Ground-based telescopes suffer from atmospheric turbulence. Even with adaptive optics, subtle distortions can mimic planets. C1 was never confirmed. It faded into uncertainty. But its position was closer to Alpha Centauri A than S1's 2024 location. When researchers plotted C1's coordinates alongside S1's, something clicked. If a single planet followed an eccentric orbit, it could have appeared near C1's position in 2019, swung outward to S1's location in 2024, then moved inward again in 2025. 3 appearances, 2 instruments, 1 possible orbit. When simulations incorporated both datasets, a narrow family of orbital solutions emerged that satisfied all observations. And they were not absurd. They were dynamically stable. An eccentricity of 0.4 would make S1 unlike any major planet in our own solar system. Earth's eccentricity is 0.016, nearly circular. Jupiter's is only 0.048, but exoplanet surveys have revealed many worlds with far more elongated paths. Nature does not require circularity. In fact, in binary star systems, gravitational perturbations can pump eccentricity over time. Alpha Centauri B's periodic influence could maintain such an orbit. If S1 exists, it may not live in a gentle, stable climate. It may experience dramatic swings in stellar radiation. At closest approach, it would receive substantially more energy from Alpha Centauri A. At farthest separation, far less. Such variation would reshape the planet's atmospheric dynamics. Storm systems could intensify during periastron. Cloud structures might evolve cyclically. Thermal emission could fluctuate subtly over each orbit. We have never directly imaged such a mature, sun-like system undergoing these changes. This would be new territory, but S1 itself might not be the most interesting object in that system. Gas giants rarely travel alone. In our solar system, Jupiter hosts over 90 moons. Saturn hosts even more. Some of those moons are geologically active. Some harbor subsurface oceans. If S1 resembles Saturn in mass and composition, it may also host a system of satellites. And here, orbital geometry becomes even more tantalizing, because S1's projected orbit lies near the outer boundary of the habitable zone around Alpha Centauri A. That means a sufficiently large moon, with a thick atmosphere, could, in principle, maintain liquid water on its surface, especially if tidal heating from the gas giant adds internal warmth. Imagine a moon orbiting S1. 2 suns in its sky, Alpha Centauri A blazing bright. Alpha Centauri B shining smaller and more distant, shifting position over decades as the binary pair orbits. Seasons not only from axial tilt, but from orbital eccentricity. It is speculative, but it is physically plausible, and it hinges on one faint infrared point. By late 2025, the community settled into a strange equilibrium. S1 was neither confirmed nor dismissed. It existed as a probability cloud, a candidate bound by physics but awaiting recurrence, and recurrence had a schedule. Orbital simulations converged on a new window of opportunity. Mid to late 2026. In many viable configurations, BS1 would swing outward again, back toward a pastron, back toward maximum angular separation, back into Webb's optimal contrast region. If Webb observes Alpha Centauri during that window and finds S1 near the predicted coordinates, the case becomes overwhelming. 3 independent epochs, 2019, 2024, 2026, tracing a coherent gravitational arc. No known artifact can mimic that. No background galaxy can orbit a nearby star. No statistical fluctuation can follow Kepler's laws across years. But if 2026 yields nothing, if the field remains empty even under favorable geometry, Then S1 collapses into the realm of illusion. A rare alignment of noise that fooled even the most careful analysis. Either outcome teaches something profound, because what Webb demonstrated in 2024 is bigger than S1. It proved that the glare of the nearest sun-like star is penetrable. For decades, Alpha Centauri was considered too bright for direct imaging of mature planets. Now we know it is not. Techniques refined here: blind offset pointing, extreme contrast subtraction, aggressive noise modeling, can be applied to other nearby stars. The frontier has shifted, and Alpha Centauri is only the beginning. Somewhere 4 light-years away, if S1 is real, it continues its orbit without drama. It does not know it has become a hypothesis. It does not know its existence hangs on contrast curves and simulation grids. It moves because gravity demands it. Nothing more, nothing less. And in 2026, when Webb turns its mirrors once again toward that brilliant lighthouse in the southern sky, we will either see a faint point of warmth stepping back into the beam, or we will see nothing at all. And this time, the silence will mean something. Let's assume, for a moment, that S1 is real, not noise, not coincidence, not an artifact of optics and expectation, but a world, a massive gas giant orbiting the nearest sun-like star to Earth. If that's true, everything changes. At roughly 2 astronomical units from Alpha Centauri A, S1 would inhabit a region comparable to the space between Earth and Mars, adjusted outward slightly, because Alpha Centauri A shines a bit brighter than our Sun. Its estimated temperature, between 200 and 250 Kelvin, suggests a cold, mature giant planet, not glowing from formation heat, not scorched by proximity, old, stable, quiet, 5 billion years old like our own solar system. This would not be a newborn spectacle. It would be a fully evolved planetary environment, and that distinction matters. Because until now, nearly every directly imaged exoplanet has been young and distant. Massive worlds still radiating leftover heat, orbiting far from their stars. They glow brightly in infrared. They are easy to see, but they do not resemble our solar system. S1 would, not perfectly, but closely enough to feel familiar. Gas giants are not surfaces you can stand on. Beneath their upper cloud decks, pressure increases relentlessly. Hydrogen compresses, chemistry transforms. There is no solid ground, but gas giants are architects. They sculpt their systems. In our solar system, Jupiter's gravity shaped the asteroid belt. Saturn shepherds rings and moons are where things become interesting. Jupiter hosts Europa, a world with a subsurface ocean. Saturn hosts Titan, wrapped in a thick atmosphere, complete with lakes and rivers, though of methane. Now imagine a similar moon orbiting S1, but this time not in the deep freeze beyond Saturn. Instead, orbiting within the temperate zone of a sun-like star. A large moon with a dense atmosphere could, in theory, sustain liquid water on its surface, not beneath ice. On the surface, clouds, rain, oceans, and above that sky, 2 suns, Alpha Centauri. A would blaze golden and bright. Farther away, Alpha Centauri B would shine smaller but distinct, shifting position slowly over decades as the binary pair completes its 80-year dance. Imagine sunsets under twin stars, shadows cast in 2 directions, a night sky where Earth appears as a faint pale dot. This is no longer pure science fiction. It is a plausible astrophysical scenario, if S1 exists. And there is another implication. Binary star systems were once considered hostile to planet formation. The gravitational pull of a nearby stellar companion can stir protoplanetary disks, disrupting the slow, gentle accretion of dust and gas. For years, some models suggested that stable inner planets might be rare in such systems. But if S1 occupies exactly the region predicted to be marginally stable, then those models were incomplete. More planets may be more resilient than expected. And binary systems are common. Roughly half of Sun-like stars exist in multiple star systems. If planets can form and survive in environments like Alpha Centauri, then the number of potentially habitable systems in the Milky Way expands dramatically. This is not a minor adjustment. It reshapes statistical expectations across the galaxy. There is also something psychological about proximity. We already know planets are common. The Kepler mission showed that most stars likely host at least one planet, but those stars are distant, abstract. Catalog numbers. Alpha Centauri is not abstract. It is visible to the naked eye. It is part of human navigation history. It is the most plausible first destination for interstellar exploration. At just over 4 light-years away, Alpha Centauri is close enough that future generations could, in principle, send probes there within decades. Concepts like laser-driven light sails, accelerated by powerful Earth-based lasers, aim to reach relativistic speeds capable of crossing that distance in around 20 years. If S1 is real, such missions would not aim at an empty star. They would aim at a system with known structure, a gas giant, a predicted orbit, possibly moons, a destination with coordinates. The difference between a star and a planetary system is enormous. One is a light, the other is a place. Even without interstellar travel, proximity changes observation. A planet at Alpha Centauri appears 10 times larger in angular size than an equivalent planet orbiting a star 10 times farther away. Its orbital motion is easier to track. Its atmospheric signatures stronger. Future observatories, including the next generation of extremely large ground-based telescopes, will surpass current contrast limits. They may measure S1's atmospheric composition, methane, water vapor, cloud structure, perhaps even thermal variability across its orbit. And if S1 hosts large moons, their gravitational influence could produce subtle timing variations or brightness fluctuations detectable with sufficiently sensitive instruments. What seems speculative today could become measurable within decades. But all of it depends on one unresolved question. Is S1 real? The year 2026 is not just another observing window, it is a test. Orbital simulations have drawn a curve across time. If S1 exists, it must re-emerge near predicted coordinates. Gravity allows no improvisation. If Webb observes Alpha Centauri at that moment and finds S1 again, the case becomes overwhelming. 3 epochs aligned by Kepler's laws, a consistent gravitational arc traced across 7 years. No known artifact can do that. No background object can fake that. Confirmation would elevate S1 from candidate to world. The closest directly imaged exoplanet in history. A mature gas giant in the temperate zone of our nearest sun-like neighbor. A system close enough to imagine visiting. And if 2026 yields nothing, if the field remains empty under ideal geometry, then S1 becomes something else. A lesson, a boundary marker, proof that even the most careful analysis can be deceived by complexity. A reminder that nature guards its secrets carefully. But even that outcome would not be failure, because the techniques developed to detect S1, extreme contrast subtraction, blind offset pointing, aggressive statistical modeling, will not disappear. They will be applied to other nearby stars, bright ones once considered unreachable. The frontier does not retreat, it advances. For most of human history, stars were unreachable lights. Then we learned they were suns. Then we learned they host planets. Now, for the first time, we are resolving individual worlds around the nearest of them. not by inference alone, but by direct imaging. That progression is extraordinary. It compresses centuries of discovery into decades, and it transforms Alpha Centauri from a bright dot in the southern sky into a system with potential geography, with orbital motion, with structure, with the possibility of weather. Somewhere, 4 light-years away, if S1 exists, it continues along its path. It does not know it has sparked debate. It does not know it has been named. It follows gravity, as it always has. And sometime in mid to late 2026, it will reach a position in space where geometry favors visibility. If Webb looks at precisely that moment, we will know. Either a faint point of infrared warmth will step out from the glare once more, or darkness will remain unbroken. And in that moment, decades of wondering about the nearest sun-like star will crystallize into clarity. Because the universe does not hide forever. It waits for us to look from the right angle, at the right time, with the right tools, and for the first time in history, we have all three.